Listen up, please. Okay, let's go ahead and get started. All right. So we're going to start by talking about the way that temperature and solubility are related. We've already talked about this a little bit because we've talked about supersaturated solutions. Okay? So I think this will make sense. We don't have a lot left to do here. At the very end of this, yep, you're going to have to move. Sorry. I need you guys to split up, go back to where you're supposed to be sitting. We're not going to do this today. This is on the video right now. It's going to be very awkward for the people who are watching the video. Oh, yeah. Okay. No, I'm not saying names here. All right. So temperature and solubility. This probably makes sense to you when we're talking about solids, right? We talked about this yesterday with the Kool-Aid, with sweet tea, with the sodium acetate. What do you need to do if you want to be able to dissolve more of any of those things in your solution? You heat it up, right? Okay. Well, okay. Now, I want to make sure that we make a distinction here, okay? We talked about stirring. So let me go back to that slide for a second here. Rate. Too far. Sorry. So the things that affect the rate are the agitation, increasing the surface area, and increasing the temperature. Those things make something dissolve faster, okay? But that's not what makes more dissolve. So in other words, you can't make more Kool-Aid dissolve by stirring it up. You're just going to make it dissolve a little bit faster than it would if you just let it sit there, right? But if you let it sit there for an hour, or you stir it for 5 minutes, the same amount of Kool-Aid is going to dissolve regardless, okay? Temperature is the only one of these that will, whoops, what is that? Temperature is the only one of these that will change not only how fast it dissolves, but it will also change how much you can dissolve. Do you see the difference there? Okay? So that's what we're going to talk about now, is how we can get more of the solute to dissolve in the solvent. Okay, but again, we've already talked about that a little bit with supersaturated solutions. Whoops. Let me go back. Okay. This works when we're talking about solids, okay, like Kool-Aid powder or salt or, you know, most other things. So you've got a bunch of things on this list, and what this graph is showing, the solubility for pretty much all of these things is going up as you increase the temperature, okay? There's one thing on this list that's a weird exception to that, which is cesium sulfate. No, that's not cesium, that's cerium sulfate. And I don't really know that much about cerium, so I can't even tell you why it does that. But for the most part, with all these salts, these are all things that would be solids when you put them into water. If you increase the temperature of your solution, it's going to make them more soluble, okay? Potassium nitrate, can you guys see how steep that curve is for potassium nitrate, the green one, okay? So you can actually dissolve a lot of potassium nitrate, a lot more potassium nitrate at 50 degrees than you can at 10 degrees, right? You see the big difference there in solubility? So that's kind of what that graph is showing you, okay? Now, do you think that works for gases as well? When we're talking about gases dissolving in a solution, do you think the best way to get more gas dissolved in the solution is to increase the temperature of the solution? Okay, well, let's think about this for a second, okay? What's a really good example of a gas dissolved in a liquid? What's probably the best, most common example we have of that? Yeah, soda, right? Okay? So carbonated anything, really. So when we have soda, we have carbon dioxide that's dissolved in water, okay? So let's say, here's the scenario. You've got a friend who has a 2-liter bottle, and they come up to you and they're like laughing to themselves, like, hey, why don't you open this 2-liter bottle? Nothing's going to happen, I promise, right? Okay? What do you think they probably did to that 2-liter bottle? Okay, well, they might have shaken it up, okay? And we know that when you shake up a 2-liter bottle before you open it, what happens? And why does that happen? Why does it squirt out everywhere? It has to do with the gas coming out of the solution really quickly, right? Now, there's another way that that can happen to you. Let's say that you've had like a can of soda or maybe a 2-liter bottle of soda sitting in the back of your car for a long time in the summer, okay? So it's 90, 100 degrees outside. This thing's been sitting out there. and you open it for the first time. You're going to get very similar results as you did when your friend shook it up, right? So what is that telling us about how soluble the carbon dioxide is in water? At high temperatures, it's not very soluble. All that carbon dioxide wants to come out, and it wants to come out really, really fast as soon as you open that cap, right? So then it sprays all over you, okay? So what that's telling us is, when we talk about gases, the opposite is actually true, okay? Carbonated soft drinks are more bubbly if stored in the refrigerator. So there's a good application for you, right? That's why you should put your 2 liters in the fridge after you open them for the first time, because that will help for the carbon dioxide to stay in the solution, okay? When all that carbon dioxide comes out, then what do we call the soda at that point? It's flat, right? Okay, it doesn't have any carbon dioxide left. Okay, so unless you like drinking the just flat sugar water, which some of you may prefer that. But if you don't like that, if you like the carbonation, then you need to probably store it in the fridge, because the colder that solution is, the more of the gas will stay dissolved. Okay? Does that make sense? So by that reasoning, would a fish like a cold stream or a warm pond better?
Cold stream.
Why a cold stream? Okay, good. Because in the cold stream, there's actually more oxygen that can dissolve in the water. Does that make sense? Okay, as opposed to a warm pond. I don't know that a fish likes one more than the other, but the cold stream can support more life because there's more oxygen dissolved in that water. Does that make sense? Okay. All right. Okay, well, there it is. I didn't realize that was up there already. Warm lakes have less O2 dissolved in them than cool lakes or cold streams. Okay. All right. Pressure and solubility. So if I, let me just back up for a second here, because obviously this is going to make a difference with gases. So let's say that I have my Kool-Aid, and I want more Kool-Aid to dissolve in my water. And I don't feel like increasing the temperature of the Kool-Aid, because then it's going to be hot Kool-Aid, and who wants to drink hot Kool-Aid, right? Okay, so I want to figure out another way. So then I think, oh, maybe I can just put this under pressure. All right, so I don't know, I have a pressure cooker at my house maybe or something that can put this Kool-Aid under a lot of pressure. Do you think that's going to affect the amount of Kool-Aid that dissolves in the solution? For a solid, it really doesn't help, okay? So if you've got, if you're trying to dissolve more salt in water, if you're trying to dissolve more Kool-Aid powder in water, putting the solution under pressure doesn't really change the solubility of a solid, okay? So don't try that with your Kool-Aid. It won't work. And besides, with the pressure cooker, it's going to get hot anyway, so that defeats the purpose, right? I guess it would work for that reason because it's getting warmer. But with a gas, pressure makes a big difference, right? How do they make soda in the first place? How do they get all that carbon dioxide to dissolve in the water? Yeah, they have to put it under a lot of pressure. They basically force it in there into this bottle that's highly pressurized, and then they put a cap on it so that the pressure can't be released, right? And then when you open the 2 liter, what are you doing? You're releasing the pressure, and then what happens to the carbon dioxide? It all comes out because it didn't want to be in there in the first place. You had to force it in there with a lot of pressure, right? So the more pressure you put on a gas, the more of it will dissolve in a liquid.
Is that why it like bubbles?
That's why it bubbles. Yeah, that carbon dioxide is in there when the 2 liter's not open, but you can't see it. It doesn't start to bubble out until you actually release the pressure, right? So that's how.
And that's why after you open it, it's open.
And that's why after you've opened it that first time, now there's really no extra pressure in there. So all the CO2 that's going to come out because of the pressure release comes out at the beginning. Now, more carbon dioxide will continue to come out of that thing, especially if it gets warmer, right? So until it goes flat, until there's no carbon dioxide left. Okay. That's why you want to put it in the fridge after you open it. Yeah, you guys are learning a lot about soda right now, right? All right. What's that? When will you, okay, let's think about the things you've just learned. Fish in cold streams are happier, right? Okay, that could come in real handy. I don't know. Maybe if you're fishing. Look for the happy fish. I don't know. Yeah, maybe catch fish in a cold stream. They're going to be better because they've got more oxygen. I don't know. I'm just making stuff up now.
They'll be stronger and they'll get off of
There you go. Yeah, they'll be bigger and stronger and that sort of thing.
They'll break your hook and you'll
Well, okay, yeah. Know what size line you need for... Okay, so that's the fish thing. You've also learned to put your soda in the refrigerator, and you've also learned that if your friend comes up to you laughing and asking you to open a soda bottle, don't do it, okay? Because it was either out in the hot sun or they shook it up. So there you go. Lots of practical stuff today. The solubility of a gas is going to increase as the external pressure increases, okay? And the obvious example is carbonated beverage. The gas is dissolved at high pressures when the bottle is open, the pressure is released, and that allows the gas to come out. And that's why it fizzes. And then if the cap is left off the bottle, the soda goes flat because now it's just open to the air and all that carbon dioxide can escape. If you put the lid on, at least the carbon dioxide isn't really going anywhere necessarily.
How do you apply it?
Well, if the cap's on, it's going to get flat from the times you open it after that, right? Because there's still...
So if you just open it and then close it and leave it like
and then leave it like that, it's still, well, okay, that's a good question. I don't really have a good answer for that.
exactly, it's all full.
Yep. What's that? Well, no, because what's going to happen is that, I mean, yes, the carbon dioxide can get out there, but then if you never opened it again, I guess you have to open it to drink it, so then the carbon dioxide escapes.
So if you want to test and make an experiment, you keep it closed for a while. You open it once and keep it closed.
If you open it once and keep it closed for a while, it's going to stay, it's going to be less flat. Yeah, but it'll still be, but what happens is the carbon dioxide is going to come out and then it's going to get trapped right there, right? So it will create some pressure over that solution that would keep all of the carbon dioxide from coming out. But as soon as you open it again, then the carbon dioxide's gone and you've messed that up, and you can't drink it without opening it. Yes, ma'am. Okay, so when you shake the bottle, then open it, what you're doing is you're agitating it, and that causes some of the gas to come out, which increases the pressure, right? So then as soon as you open that, okay, it's all of this, the carbon dioxide, basically, that's coming out really, really fast. You get the foam when it's coming out really fast. I don't have any soda with me today. Okay, listen up. No. So then this is just an illustration of this, okay, and that's the foam that we were just talking about, right? That's just carbon dioxide bubbles is all that foam really is, okay? And then, you know, obviously you've got your chemistry example where if you, well, this is showing how they get the CO2 in there in the first place, right? You take this piston, this movable piston, push it down. That creates a lot of pressure here. And notice there is more carbon dioxide now inside the solution than there is up here because there's more pressure on it. Okay, that brings us to Henry's law, which is the last calculation you're going to have to do for this unit. So Henry's law says that at a given temperature, the solubility is directly proportional to the pressure of the gas above the liquid. This is going to look familiar to one of your gas laws also, right? You guys remember V1 over T1 equals V2 over T2? S is solubility, P is pressure, okay? So this is very similar to the gas laws. It's just a proportion here, all right? I don't think you guys are going to have any problems with these equations. Again, this is a lot like the concentration, the dilution equation, where you just need to make sure you have the right things labeled and then plug them into the right place in the formula, and then you should be fine, okay? All right, so we're going to use this equation to find solubility of a gas at a new pressure. So here's an example. You have these on your sheet?
Yeah.
Okay. So in this example, it says if 0.85 grams of a gas at 4.0 atmospheres of pressure dissolves in 1 liter of water at 25 degrees Celsius, then how much will dissolve in 1 liter of water at 1 atmosphere of pressure at the same temperature? That's a lot of numbers. Here's what you need to know about solubility. Usually, not always, but in this class, we're going to say solubility is in grams per liter, okay? Because this Henry's law is really only for gases that are dissolved in water, okay? Because those are the only ones that pressure really affects. So the solubility is how many grams are there in a liter of solution, all right? So what's the solubility initially in this problem? What's the solubility of the gas at the beginning? 0.85 grams in 1 liter of water, right? So we can rewrite that as that's 0.85 grams per liter. Does that make sense? Because that's how many grams there are in 1 liter. Okay, so we'll call that our S1 here. Okay, what's the pressure that goes with that solubility? It's the 4.0 atmospheres, right? So that's P1. They're asking us about the second solubility, right? How much will dissolve in 1 liter of water? So that's our X, okay, or our S2 right here. And then 1 atmosphere of pressure is going to be our P2. And then you just plug it in. All right, so the formula again is S1 over P1 is equal to S2 over P2. So then you just plug in 0.85 grams per liter over 4.0 atmospheres. Uh-oh. He's being really slow on me here. Do you think the pressure units matter here? Well, they matter in some sense, right? How do they matter? I mean, does it matter that I have atmospheres? Not necessarily, but if I have atmospheres for one, and then I have something different for the other one, then I have to make sure my pressure units match, okay? Which they do. On these problems, your pressure units are going to match. I'm not trying to test you now on whether you remember how to do pressure conversions or not, because it's been a while since we've done those. So that's equal to S2, or you could call this X. If X helps you be less confused because it looks more like an algebra problem, just use X. All right? Just need to make sure you know what X is at the end. And then that's 1.0 atmospheres. All right? So then we got to remember here, algebraically, how do we solve this?
I got it. Here we go.
Where's my calculator?
You do 0.85 1
0.85 times 1
divided by 4.
divided by 4.0. Okay, so what we're doing is cross-multiplying, right? Okay, so then you cross-multiply here, which you only do that when there's an equal sign in between them, right? So I multiply the 0.85 by 1, so that's just going to give me 0.85, right? That's equal to S2 times 4.0. And I'm not worried about the units right now. We'll figure out the units at the end. So then I divide both sides by the 4.0. That'll give me my new solubility, okay?
I don't know what liters or what.
Okay, so here's the tricky part maybe is figuring out the units, right? Remember, solubility is in grams per liter, okay? So when I work this through, actually I probably should have kept the units on here as I was doing this. The 0.85, that's grams per liter. And then we ended up multiplying that by the 1 atmosphere, right? 1.0 ATM. See, I don't have enough room here. That's equal to S2 times 4.0 atmospheres. So then when I divide this by 4.0 atmospheres, what happens to my units? The atmospheres cancels out, right? And that leaves me with grams per liter.
You'd leave it as grams per liter?
Yeah, that would be your solubility. Now, they are asking how much will dissolve in 1 liter of water. So you could say grams per liter, or you could just say grams, right? Because they're already saying how much would dissolve in 1 liter of water. Either, sounds reasonable. Yeah, 0.21. And that's grams per liter. That's your solubility. So then technically the answer to the question would be 0.21 grams will dissolve in 1 liter of water. Okay? Now, it's probably good to think about this and see if it makes sense. Is that solubility higher or lower than the one we started with?
Lower.
It's lower. Does it make sense that it's lower?
Yeah.
And why is that? Okay, it has a direct relationship with the atmospheres, right? Okay, so just think about this. We had 4 atmospheres of pressure over this gas, right? Now we only have 1 atmosphere of pressure. We've decreased the pressure. That's like opening the soda bottle, right? So when we open the soda bottle, what happens to the solubility of the carbon dioxide? It decreases, right? Because all the carbon dioxide comes out of the solution now. So it makes sense that our solubility would be lower when we lower the pressure. Okay. I don't know if we even need these other couple examples, but maybe we can work through it. 0.55 grams of a gas dissolved in 1 liter of water at 20 kilopascals of pressure. How much will dissolve at 110.0? And then actually, let me look at the other problem here.
I don't know what it is.
Okay, we'll work our way through these then. Okay, so again, what's our solubility on this first one? 0.55 grams per liter, because this is in 1 liter of solution. So that's our S1, okay? What's our P1? Yeah, 20.0 kilopascals. That's our pressure with that goes with that solubility, okay? And how much will dissolve at 110? So that's our P2. Now, this is really very similar to the last one, right?
I kind of confusing when it says dissolve. I thought you like added those.
No, it's just saying that, that's how much is in there, so that's the solubility. All right, so then same thing as before. You're going to end up with 0.55 grams per liter divided by your first pressure, which is 20.0. And again, it doesn't matter that it's in kilopascals. As long as both of them are in kilopascals, we're fine. Then we're solving for S2 again. And the second pressure is 110.0. All right, let's stop and make a prediction here. Is this number going to be higher or lower than the original solubility?
No, higher. Higher.
Yeah, because what are we doing to the pressure? We're increasing it. So we're going to push more gas into the solution. More of it's going to dissolve. So the solubility of the gas is now going to be higher. Okay? That's the prediction, at least. We'll see if that mathematically works out. Basically, you just cross-multiply here. So you take the 0.55 times 110 divided by 20. Should give you a solubility now of 3.0. grams per liter, and that's the right number of sig figs. And that is higher than our original solubility, so that makes sense. Okay? All right, one more that's a little bit different. A gas has a solubility of 0.66 grams per liter at 10 atmospheres. What is the pressure on a 1 liter sample that contains 1.5 grams of gas? What's that? Okay, so now we're missing a pressure instead of... And it may be a little bit difficult to see that just because of the way the question is worded, but I think this should make sense. What's our S1 here? 0.66. Okay, so that's our S1. Then our P1 must be 10.0 atmospheres. Okay, now this time they're actually giving us our S2. Does everybody see the second solubility here? Okay, 1.5 grams of gas in 1 liter, so that's 1.5 grams per liter. That's our S2. So then the only thing we need is the P2. What's the pressure? All right, so same thing, you're just solving for a different variable this time around. I'm going to erase this up here and solve it up here so you can actually see it. Divided by 10.0. That's equal to 1.5 grams per liter divided by P2, or X, again, however you want to do it. So then you just have to be a little careful when you're cross-multiplying. It's going to be 0.66 grams per liter times P is equal to 1.5 grams per liter times 10.0 ATM. That's supposed to be a point there. It looks like a line. Here, I'll fix it. All right, so then we just divide both sides by the 0.66 grams per liter. So then what happens to my units here? Grams per liter cancels out, right? So that leaves us with ATM. And anybody have the number there? 23. The 0.66 only has 2 sig figs because that first 0 doesn't count. Well, yeah, you go with the lowest number of sig figs when you do your calculations. So say it again. Is it 23? 23, okay.
22.72.
Okay. So it takes 23 atmospheres to increase the solubility to that amount. That's a lot of atmospheres.
What's it also?
Well, I mean, we're starting with a solubility that's already at a really high pressure, right? So it's already 10 atmospheres. So to get it even higher, we're going to have to increase the pressure even more. Okay, that's pretty much it for Henry's Law. I'm going to give you guys a worksheet on that. We'll take a quiz at the beginning of class tomorrow, and then we're going to get started on a lab that will take us at least Thursday and Friday. Oh, this could time out badly. Well, no, we're going to do one after this, acids and bases, which I think you guys will enjoy. It's kind of fun. You get to work with some pretty colors. Okay, so that's it for the notes, right? That's the last thing on your notes, isn't it? Okay. All right, so I'll give you that worksheet, and then we'll go from there.